Okay, I'll move on to the second demo, which is running some more complex actual works. So here I want to represent some two sample systems in analytical network, which is DGX2 pods and cloud TPU architecture. And I want to run VGG16 and GPT-3, for example, workloads and compare the results. So this is the NVIDIA's DGX2 architecture at the core. So each DGX2 box has 16 V100 GPUs in it, and they're connected via NV switches with NVLink. And they are being scaled like throughout, inter boxes, they're scaled out through 100 gigabit InfiniBand. And this 100 gigabits is shared per 2 GPUs. So per each GPU perspective is effectively 50 gigabit bandwidth. So the NV switch has 25 gigabytes per second. And per each GPU, they have 6 NVLinks. So in total, each GPU is having 150 gigabytes per second bandwidth, and they are being scaled out using 6.25 gigabytes per second InfiniBand switch. So this DGX2 can be represented as a D switch, and each DGX box has 16 GPUs in it, and we want to simulate 16 such DGX boxes, so 256 GPUs in total. And the first dimension, which is NVLink dimension, has 6 links per each, six NVLinks are outgoing per each GPU. That's why the first dimension link count is 6. But the second dimension, we are only using 1 link through InfiniBand. That's why it's 1. Link latency, I just set it to 500 nanoseconds per each dimension. And the link bandwidth per each link, the first dimension is NVLink, which is 25 gigabytes per second. And the second dimension is InfiniBand, which is 6.25 as we calculated before. And this is the corresponding DGX2 system info file. Here, the major change is the all-reduce algorithm has now become hierarchical, and because it's 2D switches, we're just using halving doubling for the first dimension and also halving doubling for the second dimension. And unlike DGX2, this is the Google's TPU2 architecture, cloud TPU architecture, which has 256 TPUs in total, which are aligned in 16 by 16 2D torus. And here, each dimension has the very same bandwidth, and all these links are called inter-core interconnect. And in their paper, they claim the bandwidth of this link is 62 gigabytes per second. So again, we can abstract this topology and create this network input file, which is 2D torus. So each dimension is a ring, and there are 16 and 16 GPUs, TPUs in there. And here, the number of outgoing links per each GPU is 2, because it's ring, not switch. Link latency, I just set it to 500 per each dimension. And the link bandwidth here, this first and second dimension has the very same bandwidth, which is 62 gigabytes per second. And again, I also create some corresponding system input file. Here, the change is the all-reduce algorithm is now 2-dimensional ring algorithm, because it's 2D torus. Then we have to represent the workload. And if you remember, the workload consists of 3 phases: forward phase, input grad, and weight gradient phases. In each phase, we should specify compute time, communication type, and the size of the communication. So here, for example, I'm gonna just represent how to represent the VG16 workload. So VG16's first layer is a matrix multiplication, and the matrix size is shown here. So if we do the math, the total number of operations is about 173 million operations. And TPU version 2 has 46 teraflops on their data sheet. So if you divide this total number of operations by the TPU version 2's flops, it's about 3,400 nanoseconds. But this is just one way to estimate the compute time. We can definitely use other tools like GPU simulator. We also offer ScaleSim, which is a TPU-like systolic array simulator. And we also upgraded the ASTRA-sim to even represent the different ways. It's a lot of ways to measure that. And the communication size, here is a simple CNN with all data parallel, so it's fairly straightforward to calculate. The number of the filter size is about 1800 parameters in the first layer. And if we assume each parameter is 2 bytes, then the communication size is about 3.5 kilobytes. So with these information, I can represent the first layer of VGG16. So the compute time of the first layer is about 3,400 nanoseconds. And because it's pure data parallel, we don't have any communication for forward or input gradient passes. But for rate gradient, we have an all register collective with 3.5 kilobytes of data. So if we repeat these for every layer existing for VGG16, that's how we abstract the VGG16 workload into file. So to show it here, I give it in this exercise 2 inputs workload. And this is the full workload of VGG16. So it has multiple convolution layers and 2 fully connected layers in the end and the prediction layer. So this is how we can represent the workload info file. And this compute time, as I explained before, is based on the teraflops of TPU version 2. So instead of making another info file, workload info file for 300, we can, just like the communication scale, use the computation scale. So from their datasheet, 300 is about 2.4x faster, meaning the compute time of 300 is effectively about 0.4x of TPU version 2. So we can still use the same workload of TPU version 2 to simulate the DGX boxes, but we can set the compute scale to 0.4 so that we can shrink the compute time appropriately. So now that every script and input corresponding input files are ready, we can just go to exercise 2 folder and run this VGG16 workload. So let me do it here. CD exercise 2, exercise 2. So it's running VGG16 with DGX toolboxes with 256 GPUs, and also cloud TPU with 256 TPUs. And also I offered the script to plot this as well. So we can plot to the shrine of pi. Just on here. So the result is saved in this directory. And this tutorial result is having 2 rows corresponding for each configuration. And this is the stack bar plot for compute time and the ASPLOS communication time. So this bar length representing the total training time for each iteration. So yeah, I just copy and pasted the results here. So here the total time was pretty similar. So DGX2, each GPU is more powerful than the TPU. So the compute time was shorter, but the second dimension of DGX2 boxes, the InfiniBand, which only had 6.25 gigabytes per second, become the bottleneck. So the communication was much larger compared to the TPU, cloud TPU, which has 62 gigabytes per second per each dimension. That's why total their training time was roughly similar, but the trend is different. So TPU took more computation time, whereas DGX2 just took more communication time. So with that, we can also represent GPT-3 workload as well. Here, GPT-3 has a lot of layers, but effectively, we can just calculate the first 3 transformer layers here. That's what I did on the very same 2 topology configurations. So let me show you how I represented the DGX here. Exercise inputs workload. So yeah, so this is the representation of the GPT-3 workload given. So here I did the same thing. I represented computation time, communication type, and the communication size. So I can run this by running exercise 2 script. It's taking much longer than BG because it's larger workload. But it finished. So let me plot using the same script. So the plot is dumped. So the result can be checked. Here, the tutorial result is properly dumped, and the plot as well. So here, the computation trend is the same. GPUs are much faster than TPU in effective